let's go to Ross Small now.
Well, so basically, we obviously can't let you all know exactly how the Pi X works. We're kind of keeping that kind of to ourselves, but basically I made a pretty crazy machine that kind of hopefully should explain what's going on, but in a kind of a clunky way, but it should be able to more visualize what's going on. But in the Pi X, obviously it's not as ridiculous as this. The Pi X is actually way more efficient, better built, but essentially this is what it is. This is what it's doing. So in any I probably should start this out first. So you know, any object wants to move in a straight line unless it's acted upon by anything else. So even a gyroscope, nothing wants to go around in a circle unless it's being affected by another object. So what's happening in a gyroscope is you have two different points that are connected through what's called the center of gravity, and they're basically dancing around, call it dancing around each other. They're in a balance. So if you did the most fundamental level, each point in a gyroscope, there's only has to be two. That's it, just two. Obviously in a gyroscope, there's trillions of points all around the gyroscope, but there only has to really be just two. So if you graph that on an X and Y axis, you can think about the 2 points. They're only going up, down, left, right. That's it. There's nothing else they're doing. So furthermore, as one point is going up, the other point's going down. So one point's going up to the right, one point is going down to the left. And it reaches the bottom like this. One point's going to the right and down, the other point's going left and up. So they're always doing the exact opposite reaction of each other. 2 points on a gyroscope. So all you have to do is focus on just those 2 points that are exactly 180 degrees separated from each other. So that's what the Pi X is doing. It's taking a gyroscope and it's just focusing on just the 2 pinpoint microscopic little dots, whichever ones you want to pick, but they have to be through the center of gravity and they have to be the 2 balance points, exactly 180 degrees separated from each other. So that's basically what's going on. So this machine right here does that, but I could not do it with one gyroscope. Mechanically, it's impossible. So you can see I have a chain drive in the middle with 2 motors. So basically I cut a gyroscope. That's actually a treadmill gyroscope. It's got a big piece of steel around the end. So the weight is, the most of the weight is around the end in a big steel beam, a bar that goes around in a circle. So I cut that in half. So first off, you have to think about that as one gyroscope. So you got to get it out of your mind that that's 2 I know it looks like it's 2 gyroscopes, but they're connected by the same shaft, and it's a keyed shaft, and it's over a 1-inch shaft. So they're locked in place permanently. So that's essentially 1 gyroscope. I know it looks like it's 2 gyroscopes, but it's just, you got to think about it, it's 1. So it's 1 gyroscope with two points that are 180 degrees. 1, 2, 1, 2, 180, and they go through the center of gravity right there in the middle. There's 2 points. So now we can focus on this point because now I've got it to where the drive shaft is in the middle, and I can focus on each gyroscope separately, and I can get access to them and do what I want to do to each side. So that's what this is, a learning aid. It's a training aid to show you what the heck is going on with the Pi X in Bryan St. Clair's invention. And really, this is the Mach-1 1 from Mike Marsden. He's the guy who actually invented this whole theory to begin with. His name is Mike Marsden, Michael John Marsden, the Mach-1 1, spelled M-A-C, which stands for macroscopic, Quan, is for the quantum, and then just ones because he's making a 2 and a 3 and a 4, and but basically it's called a macroscopic version of the inner quantum workings of matter, because this is essentially how matter works. Um, Everything's in balance. So basically, that's why he called it a Mach 1. He says it's, obviously matter is a microscopic version of matter because that's what it is. It's microscopic. This is like economics, the larger one transaction of you buying a cookie for $1, that's microeconomics. But macroeconomics is like the Federal Reserve raising and lowering interest rates and a large, so they're sitting in a building. Basically, this is the larger scale of it. It's, showing you physically that's the whole idea. That's why he called it Mach 1. So just so if anyone's ever wondering, why is it called the Mach 1? It's a macroscopic version of the inner quantum workings of matter. That's basically the idea behind it. But should I just show physically moving it a little bit?
Yeah. Can you do a demo? Can you turn it on and power it up and all that, or?
Yeah, I'm going to turn on I got 2 motors. One's a really powerful motor that's not as powerful, but they're both like 10 horsepower, almost 10 horsepower. So they're both pretty powerful motors.
Yeah, fire it up, make some noise. Fire it up, make some noise. Yeah, and then let me know. After you're done doing your demo and all that stuff, let me know where things are at, and we'll do Q&A, and we'll have people, and again, don't give out anything that's too proprietary, but as much as you're able to answer in terms of questions, that's awesome.
At this point, we don't really think we're going to patent this thing because it's so crazy. I don't know. Because first off, this would never fly. I don't think it would ever fly.
It looks like the old bootstrap Cox type stuff from way back.
It's like 290 something pounds. It's just really big and behemoth. But I do have a plan to put, turn it on its side and put wheels actually attached long, have a whole platform of wheels and take this out to a parking lot and actually hook it up to electricity and then just see if it could propel itself sideways in a parking lot. Because if this has 5 pounds of thrust, that's not like a whole lot, but it's enough to get this thing moving and say, hey, it's got 5 pounds of thrust or 10. Hopefully, I'm hoping it'll get 30 pounds of thrust. Hopefully. Yeah. And then it could really get cooking. You know what I mean? I want this thing to accelerate as fast as a Honda Civic and get up to 65, 65 miles per hour. It's obvious that it's doing something. It's creating some type of thrust. There's nothing's moving the wheels. It's all going to be just inertia inside those gyroscopes, So another thing I want to throw out is the whole idea of rockets is, I've always said this, the rockets is you're throwing a lot of mass back in one direction so that you go in the other direction. So, but you're not just throwing it, you're accelerating it in one direction. And then you're accelerating the opposite direction. So in a gyroscope, it's a lot of mass going around and around and around in a circle. So it's the same idea of throwing lots of mass, but instead of in a straight line, it's going in a circle. But see, that doesn't work because a gyroscope just gets up to one speed and it's not accelerating. So you have to be accelerating faster and faster and faster. And while you're accelerating, then you're getting linear thrust. This machine does it. Well, you could do it for acceleration or deceleration. So after you get the gyroscope up and up really, really fast, like 10,000 RPMs, and then all of a sudden you put the brakes on, you slow it down. While you're slowing it down, the machine is getting momentum. It's getting linear thrust. So, but the idea is to do it from both acceleration and deceleration, because obviously you can't keep doing that. You can't spin a gyroscope to 1 trillion RPMs or the gyroscope will explode eventually. So you have to figure out a way to accelerate and then decelerate it. So this machine, this is the crazy part about it. It accelerates and decelerates exactly like a wave. It does it 4 times per revolution. So if you think about a wave, it's, deceleration, acceleration, deceleration, acceleration. deceleration, acceleration, deceleration, acceleration, decelerate. So it's basically like this. That's all a wave is doing. It's decelerating, accelerating, decelerating, accelerating, decelerating, accelerating, decelerating, accelerating 4 times per wave. So that's basically what this machine is trying to do. It's recreating a wave. It's accelerating and decelerating literally you have to do it this way 4 times per rotation, which is not easy. It's really difficult. And that's what Bryan St. Clair's machine does, the Pi X. It also accelerates and decelerates well, it's supposed to. We think there's a problem. We think it might not be right now. That's why it's not working properly. But once you get a machine, you figure out, and you can't do this with electric motors. You can't turn it down and turn it up, turn it up. It's impossible. You have to do it physically. You have to do it with some type of physical mechanism. And we do it with springs. Ultimately, one of these days, I'm going to build a machine that doesn't use physical springs. It uses magnets. So if you take 2 north magnets, they'll repel each other like a spring. So it acts like a spring. Or if you bring it together, it's sort of like it accelerates together. So you could basically take magnets and pretend like it's a spring, but you don't have that physical wear. Like this machine actually has a physical spring that's stretching and stretching, and eventually it's going to go out, it's going to break. So that the ultimate goal is to get this to be magnetized so that we don't have any parts that'll break or anything. But let me just kind of show you. This would be the one point. So this is the first point on the gyroscope. So 180 degrees from that would obviously be here. But remember, I'm talking about, don't think about this as 2 gyroscopes. Think about it as 1 gyroscope. So here's the other point. It's on the other side of the gyroscope. Right. So another point I want to make is the force has to be perfectly linear. The acceleration forces and deceleration forces against the gyroscope has to be exactly perfectly straight at all times. And that's the whole point, because you're trying to go get linear thrust. That's why all these other guys, in my opinion, Dean Thornton, David Kalishaw, all these other people have failed because they're thinking in circular logic. They're not thinking in, you're trying to go straight, so you want to have straight energy. So ultimately what's really happening is you're expending energy in a straight line. So we all know, E equals mc squared. So energy is mass. So it's the same thing. So if you could figure out how to expend energy in a straight line, it's the same concept as if expending matter in the same. That's ultimately, it's hard to explain. I know people don't like to think about, Einstein and all those equations. And some people say, oh, that's a microscopic amount of energy, for amount of mass or whatever. That's ultimately what I feel in the end. That's the best way I can explain it to a conventional physicist, is that E equals mc squared. So you're expending energy in a straight line against the gyroscope. And that's the best way I can explain to a conventional physicist how this thing works. So down here is a spring, an extension spring. Let me take it back. And you can see it's so well built that I can actually turn it with my hand. Actually, let me get it. Video back. Can you see it good? Is it? So this arm, this beam right here, this is what makes this energy transfer perfectly straight. So the beam in this particular machine stays perfectly straight at all times. See how it's perfectly straight? So that's the first point, is it's perfectly straight. And then the second point is I haven't finished the other side. This is halfway built. So I've only finished the first side here. I still have to finish the other side. So just so you know, this is not fully built yet. So once the machine gets here, this is the x-axis. This is the y-axis. Once the point gets here, for this 90 degrees, it's traveling up. For this 90 degrees, it's traveling up. So notice the spring is getting stretched. It's got energy building up. It's slowing down. It's slowing down this point in a straight line, though. So it's slowing down this point, and then when it reaches this point, now this point is going down. So it's no longer going up, it's now going to go down. And this spring is going to help accelerate it down. So you see it accelerates. From here, it accelerates. So from here to here, it decelerates. Here to here, it accelerates. And then when I'm done with the machine, the other side would do the same thing. But it would decelerate this point and then accelerate. So what's happening is this point on this side of the machine is decelerating for 90 degrees, accelerating for 90 degrees. Then you switch to the other point mass that's 180 degrees out and decelerate for 90 degrees, then accelerate for 90 degrees. Then you come back to this point again and decelerate for 90 degrees, accelerate for 90 degrees. Then you switch back to the 180 degree point, decelerate for 90 degrees, accelerate for 90 degrees. Then you switch back again. So you're doing this 4 times per rotation. So deceleration, acceleration. Deceleration, acceleration. Deceleration, acceleration. Deceleration, acceleration. Deceleration, acceleration. So you get it? Okay. Should I crank it up with the electric motor?
Yeah, crank it up, crank it up.
All right, this is the first time, man, so I wanted to go. This could be dangerous too, so I gotta be back.
Make sure you don't have any wrenches or loose parts or anything like that, right?
Yeah,
Because I know you've been working on it, right? So
I literally just got this thing, like the spring and the wire. I just built it like a minute before I got on here. So I lubricated it. I got, bolt tightened everything down. Everything seems tight. So yeah, I'll just kind of power up.
You might want to put some weights on the wood too. Yeah.
Yeah, I've already been playing with it. So when that arm goes back and forth, the whole machine wants to twist. That's why I added a counterweight here. So I added that heavy counterweight to kind of counter-react that side force.
Yeah, I was just worried if it might tip over, right? Because it's taller than it is wide. But
yeah, it probably won't tip over. Well, if it does, I'm not near it, so I don't care. Whatever.
Yeah, go for it. Fire it up. I would love to see it. Look at that. See, this is another APEC first. We've got Bryan's demos. Now we have a Ross's demo.
All right, let's see. Should I do it like that angle? Yeah. You can see it got a little bit of crazy there.
Yeah, but you know what? It actually, it seems smooth. I mean, it's
not that it's nice. I built it so strong. I got really good bearings. All the bolts are really good and everything's balanced. Those gyroscopes are perfectly balanced. I spin them up to like 10,000 RPMs. Got them. I added all these counterweights. They're all perfectly balanced. So it's all good stuff.
Yeah, I mean, when it's running, it seems really smooth. I was surprised, you know, from looking at it, right? I thought it would jerk around a lot. That was why I was worried about it tipping over. But when you got it going, it seemed really smooth. So let me see. I allowed everybody to unmute themselves. So other folks should jump in here if they have questions. And now, do you have more to present, Ross? Do you have more to? And you were more than welcome to. We got lots of time.
I mean, I don't really know what else to explain. I mean, you know, there's a like a 1 1.25 inch big shaft down the center that's keyed. So the two gyroscopes are locked in place, so they can't accidentally, you know, come loose from each other. They're locked, so they're stuck together. And you know, there's 2 motorcycle chains, and there's 2 really powerful alternating current electric motors, really nice couplings here, 2 really expensive 112 tooth gears. These were really expensive. These are for go-karts. It's like number 40 chain, I think. I forgot. But yeah, you know, this, I made all the whole slider system. I made it by hand. I just made it myself. Just some random street sign, a stop sign from my friend's business. I get a lot of spare parts and things from my friend's junk removal company. So I got the gyroscopes from a junk removal company for free, all the wood for free from a deck job, 2 motors. I got one off this was off a cement machine. That one was off of a bandsaw. You know, this is from like a computer server room, the aluminum I-beams from a computer server room. These are just, you know, 2 random dumbbell weights that I found at, you know, Goodwill. And, you know, it's just cobbled together, basically, this random stuff at home. I didn't even weld. I'm not even a welder. So Bryan's a welder. I just bolt everything together.
Yeah, again, when you turned it on, it ran real smooth. Do you want to try and turn it on again, or?
Yeah, I'll show it real quick. I mean, let me see. Yeah, I might like not let it go up to too high speed. Oh, you notice that this spring overpower. If I started here, the spring overpowers the motor. The motor can't stretch this spring. This is a garage door spring. So you have a lot of energy to, like, you know, get it up. And then it accelerates it. So it decelerates it here. Like decelerates it here, and then it accelerates it here. So I got to start it like over here to get some momentum to get it going. that good enough?
Yeah, I mean, this is just kind of my perception, but it makes a lot of noise, right? But in terms of actual operation, it seems pretty smooth. I would say from when I see, great job, man, great work. You know,
I'm just wondering, like, how much. Think about how much like upwards pull that is trying to lift the machine up down here every time it catches the gyroscope and slows it down. The whole machine is like getting this kind of jerk upwards, and then around the back you accelerate it, so you get another pull.
so Ross, when do you think? So you mentioned you've only got one of the motors operational, and so this thing is only kind of going at half. I mean, it's only going half. When do you think you'll have this ready for like a full demo?
I don't know if I really will. I mean, maybe I'll take a video of me out in that parking lot and I'll put it on YouTube and let y'all see.
Yeah, well, the reason I ask is I'd love to have you back to present on the machine and the progress you've made on it, and you know.
Yeah.
I mean, we are your people. So
yeah, I've been on the last several APECs for a while now, so
yeah. This is your audience, man. These are the folks who can help. These are the folks with feedback, with the, you know.
I've been following Inertial Propulsion since 1999, so I feel like I have to show people like how it's really done, because everybody keeps thinking like Thornton and Lathwaite and Dean. Now I call them hula hoopers. They're trying to hula hoop themselves into space with this round, like asymmetric, like accelerate forward and have momentum, have centrifugal force and propel yourself forward. That's not how it's done. It's impossible. You can't do it that way. It's not going to work, because when you accelerate something forward, you accelerate backwards. So you're not going to get momentum by doing that. Like a Dean drive, like you're not going to get momentum, because every time you accelerate, you get accelerated back. So you're never going to get yourself a forward momentum. So everybody is wrong and they're all stuck. We call that the blind, Mike Marsden calls it the blind alley. Everybody is stuck in this blind alley. And we want to get you out of your blind alleys. You're stuck in your blind alley. You have to get out of that type of thinking. You're never going to be able to do a Dean drive, a Thornton. All that is bullshit. None of that works. All that is crap. They wasted their whole lives. They will never, that cannot work. And all they're doing is proving to the conventional physicists, oh, see, I knew it. I told you we were right. It's impossible. And because you keep proving them right. You have dumb ideas like that you could have more centrifugal force in front of myself and gain momentum in the front and less in the back, and more in the front and less in the back. That's not how it can work. That's wrong. You have to get out of that type of mindset. So that's part of the reason why, me and Bryan want to kind of shed some light on this whole subject.
Yeah, and you guys are doing heavy duty stuff too. That's really cool.
Yeah.
Mechanics.
I grew up as a mechanic too, so
this is big. It's heavy duty. This is real. It's not tabletop stuff. So that's really cool. But yeah, I mean, it's awesome to have so many different approaches to it. And then we have Mike Gamble with us too, and he's got a bunch of stuff. So everybody's got a little bit different approach to it, and I think it's good to have so many different avenues. But I like your guys' stuff. Like
I'm still just at this point. Since I've been doing this for 23 years. I'm really convinced that you have to do it this way. Somehow I mean, there's a million different ways you could do it like this, but you have to be able to just focus on 2 points on a gyroscope, and you have to do it at 90-degree angles, and there has to the force that's generated to the gyroscope has to always be straight. You have to figure out some way to have, we call them linear tethers. So in Bryan's, it's these linear tethers that go like this, like that. So that's basically how it works. But I feel like that's, at this point, I've been looking at everything. I've tried everything. Nothing's worked except this seems to be working.
Okay, well, so let me do this. We're almost at the bottom of the hour. So let me put this on gallery view. And we still got about a half an hour until Michael. But everybody, please give Ross Small a giant hand. Ross, thank you again for the demo, man. And thank you for walking us through everything. Thank you for the demo.